Today, I propose to deal with one of the major challenges for SOC integrator is how to reduce safely the power consumption of a SOC. So let me introduce our approach step by step. So I will present you step by step. So first, the use of panoplies, the diverse power synoptics usable for low power SOC, and the design flow for low power SOC. And we will assess the technique of power synoptics in 65 nanometer example. So before to start, I would like to introduce Dolphin integration briefly for those who don't know Dolphin integration yet. So this is a French company created in 1985, providing silicon IPs for mixed signal SOC. So we have product from 0.18 nanometer until 0.18 micrometer to 28 nanometer. So we are more than 135 design engineers working, designing IP silicon product for different subsystems, high resolution audio, high resolution measurement, low power storage, and low power microcontrol logic. And the major differentiator is the flexibility of the IP configuration. So first, for more than 25 years, Dolphin develops a unique know-how to offer differentiated library elements, memories, and standard cell. Now, Dolphin today extends its offering to panoplies to handle one of the issues in delivering scattered library elements. I mean to ensure the functionality of integrated IP, where the difficulty of the implementation lies in the connection or communication between the different elements. So the panoply definition today is composed of a comprehensive set of silicon-proven standard cell libraries and memories with dual voltage capability and support of all existing power modes, associated power management elements for building a power-efficient SOC, so it's mean power regulators, and case study tutorial product to help the customer to integrate and to verify all those IPs together. So we introduce also the definition of the power network synoptic, we will come back later, which focus on the different voltage and power relationships between the different library elements. So each synoptic represents an explicitly proven construction of the power network for the panoply. So here, this is an example of power network synoptics for low leakage purpose. So the objective of such synoptic is not to frighten you, but is to guarantee that the different elements from a panoply will work properly together. So this is to ensure that you won't have loss of performance, loss of functionality. It's to advise the customer how to perform the integration and the verification of all those elements. So you can see you have different hotspots. The green one represents where Dolphin IPs can provide a solution. The orange one is a combination of Dolphin IPs with case study tutorial product, and the red one, or I would say, is the construction issue that must be handled by the SOC integrator. So let me review with you the different construction issues for building a low power islets. So the first one we see is the management of the power up and transition mode between the regulators, so inside the power management network. So the risk is the incorrect behavior of the SOC. I will review first the risk and we will see Dolphin solution afterwards. The second construction issue is the voltage regulator sizing itself. So there is two cases. Either the voltage regulator is undersized and you may risk power supply collapsing. On the other case, you have oversized regulator. So there is no risk, but the solution is completely inefficient. The third construction issue is the power management network sizing. So this construction issue is relative to define the correct number of regulators on the partition in Islet. The risk is loss of area in your SOC, the high number of external components, the increase of bill of material. Another construction issue is the management of the power-up sequence at the Islet level. So it's when you're tuning on all the power switch together. So here you have the risk is the collapse of the power supply and a dysfunction of neighbor islets. So another construction issue is to design and size the power switch for a given memory cut, because you can have some islets with memory and you want to switch off this memory. So there is two different alternatives. The risk is higher drop at the stock level. So either the IP provider provides you the memory and he has to build by himself the switch, or the IP provider can provide him the memory with the switch. Another construction issue is when you want to directly connect a part of your islet, the part which is always on power, you need to have a direct connection to the battery on one side, and you need to have compatible with the rest of the SOC. So you need to have voltage standard cell library for that. So the risk is if your block always on is very leaky, the lifetime of the battery will be significantly shortened. So another construction issue is lowering voltage for further power saving. So this is the dynamic scaling of the supply voltage. So here is the purpose is, when you have different regulators and you want to switch from one to another, you have to be careful, because you can provoke overshoots or undershoots upon the voltage change. Another construction issue is the insertion of hard block within the standard cell when you want to perform composite islets, including standard cells and memories. So for that, if you don't take care, the risk is the higher drop. So to limiting this risk, the main implementation is to perform, for example, ring implementation around your islet. So let's focus on some of those construction issues on Dolphin solution. So I mentioned as the first one, the management of the power-up sequence and transition between the regulators. So the risk is the incorrect behavior of the SOC. So our solution, for example, in this case, this power synoptic is focused on leakage purpose. So you have in the power management network, you have one switching regulator, ESR, and you have a QLR. So the ESR is to work for to supply for the normal mode, and the QLR is for the retention mode. What you want is to switch off the switching regulator when the QLR works. So this requires to know how the different regulator works, and you have to handle the forbidden states between those two regulators. So the solution is to provide you those both regulators in the same IP with what we call a regulator control unit to control the different transition between the different regulators. So this can ensure you the optimized functionality in normal mode and optimize leakage in retention mode. The second construction islet is the regulator sizing to supply the logic islet. So the purpose here is to have the correct size of your power management network. You don't want to waste area, and you don't want to have power collapsing. So here what we propose is to help the customer through case study tutorial product to build the regulator together with the islet and to perform the adaptation of the regulator to the islet or the reverse, the islet to the regulator, it depends. So this will be able for you to perform simulation to ensure the transition mode. The third construction issue I would like to focus on is the power management network sizing, so the complete power management network sizing. You need to define the number of regulators. Traditional approach is you start from specification or you use PMIC. What we work within Dolphin is to define a structure of this power management network. First, to defining what we call an interface for the power distribution. On one side, so upstream regulators will be focused on optimize with the source. On the other side of the EDP, you will have regulators optimized for the islet. So, we provide you with simulation models and simulation methods to be able to assess at early stage the performance of this power management network. So we provide you all those techniques and simulation transfer know-how to enable you to build the appropriate power management network. You certainly know that the power management networks can be selected among several criteria, like limiting the number of external components, the area, the power consumption you want to save, or the number of modes, power modes you want to be available in your SOC. So in this example, the retention alternative regulator can be a downstream regulator because it's focused on optimize for the islet in retention mode. Another issue, perhaps one of the most familiar for you, is when you perform extension on retention islets. The construction issue is when you power up all the power switch, you have a current surge due to hundreds power switch working, turning on together. So the traditional approach is to limit this higher drop by power up 10% of the power switch, then 90%. Today, the Dolphin solution is through a patented pending for the specific standard cell, which we call transition ramp cell, to control automatically the power-up sequence and the higher drop in the extension islet. It works like by measuring the higher drop and to limiting the inrush current. So another advantage of this solution is that the SOC integrator doesn't have to deal with the power-up sequence and doesn't have to perform higher drop verification afterwards. So, just to try to fix some, I draw some examples through a SOC in 65 nanometer. So here is to show you an example of different power management network focusing on different criteria. So here is an example where you have different modules. You have a modules always on, you have a modules for extension, module 3. You have a module 2, a little bit more complex, consuming 200 milliwatts. It can be a CPU inside. And the module 1, very large one, consuming 600 milliwatts. Could be a DSP. So here you have in the power management network only an external PMIC. Other alternative for building your low power SOC is to introduce with the standard cell offering power switch, level shifter and isolation cells to perform extension of your islet. So here you have other alternatives. You can perform nominal voltage and extension. The other power synoptic power management network we introduce, so we don't have any more external PMIC, but we introduce switching regulators for module 2 and 3 and our specific regulator package for the module 1 because it will be in retention mode afterwards. And here, this is another one where we introduce what we call the interface of distribution power. This one enables to play and to have different power modes for the different islets. So you can see that you have more regulators, but you have more power modes available. So if we just look at the trade-off, I would like to highlight two important things. Regarding the different power management network we just saw, you have access to different number of potential power modes depending on the power management network you select. And you can see that for the west, because when we call about west, it's because we put on the source side, so it's the west. In retention mode is very limited, for example, with the progressive one. But you can see that the area in the SOC will be increased. So this is really a trade-off regarding your criteria for the low power. If you want to have access to different low power modes, you have to choose this progressive approach. It depends on your criteria. So we have viewed the panoplies, we have viewed the power synoptics to build your power management network. We deal with some construction issue. And now I would like to show you, so it's a little bit complex, but you have here in gray the common design flow and the step added with Dolphin solution, mainly based on modeling and simulation of the power management network and how to adjust at the different stage the different parameters of the power management network, including the Islet implementation. Okay, so you have silicon IPs, you have a DA solution. What we propose to add is a recipe, which means the transfer of know-how through our case study tutorial. Because when you see here the different steps, EPLAM simulation, we don't just say EPLAM simulation. We provide to the customer the different models required for this type of simulation and how to perform this simulation. So this is the heart of the CTP product. So here it's a step-by-step process. With the customer, we propose to first understand the issue, then create the schematic with appropriate models and parameters, perform simulation on a generic case, and after adapt the parameters of the model to the customer case, to the stock integrator case, and to set up the simulation for performance assessment. So here is examples of CTP we have selected to help the SOC integrator to perform low power construction. So here the CTP will focus on the power management network architecture. The transfer of know-how will be based on different items. How to select the best architecture for power management network, depending on your criteria. Understand what is the interface for distribution power, and the various types of power regulators. I mentioned switching regulators, but you have linear regulators, and you will have linear regulators focused for noise, focused for logic islets. To understand the difference between PMIC and PAM network, and to evaluate and assess the power consumption of the different loads on the network. So this is the first CTP we propose. The second one is to perform the optimization of the pair regulators on Islet, is to avoid to have an upsized regulator for the logic Islet need. So the transfer of know-how is composed of how to use our model, so we call electrical performance logic and analog model, how to verify by simulation the compatibility between the regulator and the Islet, and to estimate the airdrop budget. Size also the capacitor by partitioning the budget provided in the regulator specification between external capacitors, if any, and the internal one. You will also have in the CTP what we propose is to perform a simulation from the source until the islet, so it compounds as well models for parasitics. So this is an example of EPLAM simulation you can have. And the last, which should very be interesting for SOC integrators, is the Power Islet implementation guidelines we propose. So during place and route task, we describe step by step how to create your Power Islet with our solution, including the TRC cells, and define the number and the size of power grid, describe how to implement the TRC cell, and to get accurate value of the islet power consumption. So this is a step-by-step process to help you to use our panoply. So let me summarize this step-by-step approach. So we have first to define the power network architecture to assess the power consumption gain at early stage. You have to select the appropriate power synoptics to anticipate and mitigate the risk during the integration. There is a transfer of know-how through our case study tutorial product in modeling and simulation to help the SOC integrator all along the low power SOC design flow. So this is additional step to the standard flow. And panoply offering to provide a complete solution to the customer. So to remind you, the panoply offering is to provide you all elements to succeed in the integration of the different elements in building low power islet. And we propose you a very smart solution for self-integration of retention and extension islet with the click on TRC cell. That's all, thank you.